From this participation in Maker Faire, we thought it would be very interesting for 2020 and the years to come to have an internal capability to actually make tangible assets that can be used to show our work. And we decided to take advantage of other internal activities which we have been doing in ESRIN, in particular something called the Air Quality Platform, AQP, which is a custom device built with the low-cost sensors that we will go into a lot of detail in describing. And it is the work of my colleague, who I will now introduce, Massimiliano Ferrante, or Max Ferrante. We will be trading places during the presentation. You will go through the first part describing all the pieces of the AQP, and we will then go into slightly different topics, but which are, I'm sure, will be of interest to the audience. So, without further ado, I introduce Max and Massimiliano, and he will introduce you to all the details of the AQP.
Thank you, Paolo. The acronym AQP stands for RasperryPi platform, and this slide shows the first prototype that is called the educational version, AQP educational version. That is an assembly kit hardware software capable of sensing some local ambient parameters and send the data to a ESA central server. It was designed and built in ESA at the SDEO laboratory for the ESA Living Planet Symposium 2019 for educational purpose. And then we show the first platform, that is this one. This one is the educational platform, educational version. This platform is composed of chip sensors, all sensors which were all procured on Amazon, and all the material cost of this platform was below 200 euro per unit. The software that runs on this platform is open source and is written in Python and in C. The two platforms use the two different kind of microprocessor, RasperryPi and Arduino Nano. The hardware, we can consider even the hardware open, because it's possible to add electronic components or electronic sensors on this breadboard that is on the top of this kind of AQP. This platform is use a low-cost sensor for measuring 11 parameters: temperature, humidity, PM10, PM2.5, CO, CO2, NH3, ammonia, NO2, GPS as position. GPS is not a real sensor, but we can consider in virtual way as a sensor. Then CH4, that is ammonia, and then atmospheric pressure. Here we can see three pictures. The first one is the kit that we will explain later. Then you can see the guide that explains in a deeply way how to assemble all this kind of platform, starting from the three layers of this kind of AQP. And then we can see the video on YouTube that is assembly procedure video that describe with the video how to assemble this kind of platform. Now we show you the three layers. The first layer is composed of RasperryPi, that is the brain of this kind of platform. The three layers are made by plexiglass. This one is the first one. The second layer is composed of Arduino Nano and particulate sensor. We use the Arduino Nano as an analogic to digital converter, and for making some software filter to filter the data acquired by analogic converter. Then the third layer is composed by all sensors. Here we can see the breadboard. This one is the GPS. This one is temperature and humidity. This one is a sensor that is able to measure CO, CO2, NH3 and NO2. This one is a sensor that measures CO2. Then, okay, thank you. This slide shows how it's possible to make your own AQP. The first step is to buy electronic components, and you can find the list in the guide that we described before, in the page 4. Then the second step is to assemble the kit following the instruction in the guide in the video that you can find in YouTube. The third step is to subscribe to the site that is described in the bullet number 3. Then you can, once you are subscribed, you can download the software. You find two kinds of software, one in C and the other in Python, and then you have to install in the RasperryPi and the Arduino. Just copying this kind of software. Then the last action that you have to do is to check if everything runs properly. Now we can show you. We use this one to make the platform. Of course, you can assemble the electronic components when you want, but if you want even to have the same position in your structure, if you want to make, we provide you this kind of mask that allows you to make a perfect holes in the perfect position to have a physical copy of this kind of platform, even if you can use other kind of material as normal plastic to put this device on. Then, this slide shows the 4 macro AQP versions. The first one is the educational version that we have described before. Then there is the exhibition version. The characteristic is very similar to the educational version. This one is we use just for the exhibition for the demo. But today we don't use just this one. We show you all kind of a platform. Another platform is this one. We call sensor calibration. It's very important. This platform, especially when we use this kind of a sensor, chip sensor, because the scope of this platform is to verify the functionality of the chip sensor. And then the second functionality of this platform is to calculate or estimate the conversion curve from physical value and electrical value. When we buy chip sensor, often it is difficult. It's very difficult to find the proper technical documentation. So we have to define how they work, and we have to define if they work properly, and the characteristic the characteristics that we find follow the reality or not. Then the last task of this platform is to correct or align the value provided by chip sensor for comparison with the professional instruments. Even this activity is very important for using this kind of chip sensor. The last one is Lotus, that is a special unit. This one is the special unit. Later we will try to have a demo and try to explain all its capacity. Then the next slide shows the functionality of Lotus. This platform is a multidisciplinary project. Lotus is a globe that open as a lotus flower. It has 6 petals, and for each petal there is a sensor that measures the quality of the air. In the previous AQP version, we don't have a monitor inside, so it's just to understand what the platform is doing, we have to connect with the server. Instead, with the Lotus has a monitor inside, so we can check the activity of the Lotus. Then we can check the trend or the value of in real time of the sensor that are mounted on, and then we can overlay the Sentinel data or the satellite data and visualize what this kind of platform is doing. Then it's possible to see Lotus has a robotic mechanical movement. It has 12 servos that provide 12 degrees of freedom to move the pedal. Then there is an audio functionality. Then it's possible to see fine art painting of the globe. And we use, even today or generally, this kind of platform as a central node in a network of Internet of Things sensors. Let me show you how it's possible. And this platform implements some machine learning algorithms to correct, to evaluate if the sensors are properly working or not. The last bullet showed the link to see the video. Here there are other macro AQP. In the left, we can see the backpack. That is the first wearable device that we made. Is a backpack where inside we can find a AQP platform, power bank, connection to internet, and a small solar panel integrated in a backpack. This other feature shows an experiment where a child was walking along a street wearing this kind of backpack. And we made a video of this work. And using this kind of backpack, in real time, we were able to visualize the position of the backpack, and so the child in a map. You can see here the yellow spot. And it was possible in real time using machine learning algorithms to correct the position provided by the GPS. I don't know if it's possible to see or you can see, but in blue spot you can see the correction. And then we can see in real time the trend of the value of the parameter that measure the quality of the air. So it was possible to have all under control. And then it was easy to discover that this peak of the CO2 was made by a truck when the truck passed close to the backpack. And the last sentence is it's possible to imagine that that child was breathing the same air that the backpack was measuring in that moment. The last two AQP are ongoing. We are finishing both of them. One is almost finished, the automotive. Now I'll show you this kind of platform. It's composed by a cup. This is a version that we put in a car, anywhere in automotive field. It was designed just to resist to a remarkable vibration and electromagnetic noise. It's composed by this one we call cup. We made all this kind of pieces using 3D printers. Then we use this one to increase or decrease the air, the passage of the air, just to avoid the rain can go inside. You can decrease the air. Then we have the backpack. So we have the AQP. This one is the AQP version, all integrated. It's possible to insert, and then we have these three sub. It's possible to put outside of the car. Then the last one is the AQP mobile. This platform is composed of AQP with professional sensors and a rover. In this way, the rover can reach the position of the sensor, and measuring the same air condition is possible to align or correct the value provided by this kind of sensors. Next one. This slide shows 4 Internet of Things micro AQP devices. We developed this kind of device, and before I would like to show you the architecture that we use for this device. The architecture for this kind of device is really simple. We use Internet of Things microprocessor, then any kind of sensor you choose, and then you put in the middle of these two kind of components the interface to interface the microprocessor to the sensor. That's all. So it's possible to make a very small sensor and cheap sensor. This kind of device costs €5, €10, not more. And then the cost is almost just the sensor that you are using. So this kind of, this one is, we put in the garden. It's composed of solar panel. In this case, there's a sensor which is temperature and humidity. And then inside there is a battery, and then there is the switch to turn on off this kind of device. The second one is the lamp. This lamp is a standard electron network plug, so we can use as a normal lamp. But the property is with this kind of lamp, we can control the value provided by the sensor. In this case, we use the CO2 sensor. We can turn on and off the light. We use the LED, and then it's possible to control both of them remotely. The next one is CO2, we call micro USB. It's something like a mobile, but instead of the mobile, you can measure the quality of the air. In this case, we put the sensor as CO2. Then the last one is this one. This kind of, we call a message in a bottle. It's possible to see inside the small bottle the Internet of Things microprocessor, and then this kind of sensor is able to measure CO, NH3, and NO2. Putting all together. Okay. Before I show this kind of architecture, I would like to show the backpack. It's composed here, there is the AQP, then there is the solar panel, and then inside there is a power bank and 3G or 4G connection to the internet. This slide shows the architecture of the AQP. AQP project is composed of three main subsystems. The first subsystem is a website, you can see there. Then the platform here on the left, and then the satellite data. In this case, we use Sentinel data. The platform sends the data periodically to the web server. The web server visualized and georeferenced, knowing the position using the GPS on the map. And then it's possible to see the behavior, the trend of this kind of platform. Here we see all kinds of topics that are related to this kind of project, AQP project. Satellite data, Sentinel key. Educational, as you see, the educational platform, Internet of Things device, you see before, Science Citizen, Internet AI, machine learning algorithms, sensor calibration, robotics, and wearable devices, and then the automotive platform and the mobile platform, as we described before. The next slide shows the possibility how we spread this kind of platform in Europe. In fact, it's possible to know how this kind of platform are located in Europe. Then once you selected the specific platform, you can understand, you can see in real time the current value or the historical value. And then you can see the user can overlay the map of the latest Sentinel-5P data or the Sentinel-2 data.
So I will present now this part. So as Max has been showing you since the beginning of the presentation, most of our, if you want, the initial making activity has to do with air quality. with the macro AQP and all the micro IoT devices that you have seen. However, we have, because ESA is one of the main things that ESA is doing, building satellites and launching satellites, such as those of the Copernicus program, which are called the Sentinels. And some of these satellites are measuring gases which are tightly related to air quality, and that's why we have an interest also in measuring sensor data in situ. But there are other kinds of satellites which are doing optical measurements, radar measurements. So we have an interest in collecting other kinds of sensor data in situ, so also on the ground. For this, we have recently put in place a partnership with the Planet Labs. Planet Labs is a private company, one of the actors of the so-called new space, which is a fairly recent trend, but that you have very likely heard of before, because you are probably aware of Elon Musk and the work that he has been doing with SpaceX and so private satellites. Planet Labs is another of these private actors, and they have developed small size satellites, like the size of a shoebox, and they have launched this into space, building huge constellations. So they also, similarly to ESA and NASA, so the more traditional kind of space organization, they also have an interest in comparing this data that is acquired from the satellites with the data that is acquired in situ on the ground. So one of the devices that Planet Labs has been playing and working with, and we have obtained a couple of these from them, is this one here, which is it's called an Arable Mark, an Arable Mark II sensor. This kind of device is not measuring air quality like the AQP and all these micro IoT devices. It's actually measuring things like the health of the vegetation and also how far along a given crop, for example, is. So this kind of instrument is used mainly in agriculture, so by farmers, to understand the health of their crops, when is a good time to harvest, and things like this. This is interesting from a space agency point of view, because you are also using satellites to understand the same kind of phenomena. And so we have installed a couple of these. As you can see in the three pictures here, we have different zoom levels here. We have installed a couple of them here in the olive tree field that we have on site in ESRIN. And these are powered by a solar panel like this one here. And we have a close-up actually of the setup there. And we have a website where we can actually keep track of the status of the devices, if they are powered, if they are collecting data. And we have done this in the last couple of months. So we have so far collected a couple of months of data. And of course, as you can imagine, our plan going ahead is to join together the sensor data that we'll collect on air quality with the data on the health of the vegetation, to build a true Internet of Things, as we will see very, very soon. So the kind of, I have 3 examples here on this slide of the kind of information we get from a sensor like this. This one is on chlorophyll. So since now we are in autumn and winter, the kind of value we are getting is fairly low because there is not a lot of activity. Max? In this one, we have the NDVI, so it's a very popular vegetation index, which also gives an indication of the health of the vegetation. And I don't know, it's probably not very easy for you to see the scale here because it's very, very small. But the two sensor values, they are in the green range, which is fairly healthy, or let's say fairly green if you want. And if it would be yellow, it would be bare earth. So like if you don't have any vegetation, it's like yellow. We also, besides this aspect of the vegetation health, greenness of vegetation, things like this, we can also use a device like this as a simple weather station. So like measuring things like the temperature. And this is one of the examples we have here. This is a screenshot from last week, I think, when it was fairly cold in Rome. So the temperature was around 7 degrees towards the evening. And that's what you see here in this slide. So as I was mentioning before, and this is a bit, I mean, this sensor here is not an example of making and this making capability that we want to have in ESRIN. Because it's a commercial instrument used by farmers for agriculture applications. But we are nevertheless interested in building other kinds of sensors like this, or maybe inspired by this. But even more important than this, we are interested in building a network of devices and network of sensors, a network of an Internet of Things. And so what you see actually in this slide is our plan. Then it's something that we want to install next year and the years afterwards around the site in ESRIN. So this is an aerial picture, satellite picture of ESRIN, the ESRIN site, and we are planning to install 10 of these. So similar platforms to this. So the AQP that Max showed in the beginning, 10 of these nodes, and we already have the two. Now I have it here in my hand, but normally it would be installed in the olive tree field. So these are the two devices that we have here. This is the olive tree field, which is quite large, and we have 10 AQPs deployed all around the site. Each of these 10 nodes, of these AQP nodes, is not only one of these, so not only one of these platforms with the 3 levels and all the different sensors, which are many different sensors, but we are planning that each of those 10 nodes actually becomes a small subset of or a smaller network of sensors in itself. So the plan is that around each one of these, we will have in a kind of, or a star-like configuration, we will have other sensors and other devices like the ones that Max also showed, these true IoT devices. And there are 3 examples there. One of them is this one here, that you can just simply stick on the grass and on the ground. And we have the other one is a lamp, the lamp that Max showed. And the smaller one, which is which has a USB interface actually. So these devices, they will communicate with the AQP, the central AQP node, using fairly well-known protocols like Wi-Fi or networks like Wi-Fi and Bluetooth. And this is done for a few reasons. One of them is that even though the RasperryPi, the Arduino, they give you some computing capability, we don't have that same computing capability on the IoT devices. So they are more limited. And so, of course, you are also limited in what you can do with this sensor. So this is one of the reasons why we adopt this star configuration. Yeah. So go to next. And Max will, towards the end of the presentation, and just before the demos, we will talk a bit about the sensor performance and how these are low-cost sensors, and being low-cost sensors, you have to know exactly the accuracy and the quality of the data that you are measuring. But we will, this slide represents our plan already to address this kind of issue once we have the network in place, the network deployed. And the idea is that we will have moving calibration platforms. So these are platforms that can actually go around the network and to the close to the different platforms, and if necessary, apply corrections to the values. And we have a couple of these moving calibration platforms. So a drone and a rover that we actually have made. It's just a simple game for you to see. We have the drone and the rover going around the network of sensors in ESRIN. So the drone, of course, since it is able to fly, it doesn't have the limitations of the network of roads inside the website, so it can go anywhere very quickly. So that's one of the possibilities. And the other one is the rover. And the rover, of course, is contrary to the drone, limited by the roads on site. So it will take longer, a bit slower. And there is also a risk, of course, that it will be crushed by some car going around. So, of course, this kind of operation, we can do it in the context of a lab, a static context. But when these things start to be many, and you have many different locations, it's good that you have something autonomous, which will be able to move around for the calibration activities. So we are reaching the final part of our presentation before we go on to some hands-on demos. We have an ongoing cooperation with the University of Texas in Dallas, and particularly with Professor David Larry, who is a very well-known name in the world of AI and machine learning. His team, we found out last year, in the last couple of years, they also have their own network of sensors like this. They are also looking at their quality. They are also using low-cost sensors for this. So they also have the same problem that we're just talking about. So the calibration, the correction of these the values, which you can do by using instruments, but you can also do by applying algorithms, and specifically machine learning algorithms for these corrections. So the team of Professor David Larry has a very similar scope, very similar goal to what we are trying to do here. So they have their own network and they want to do calibration. Let's say, whilst we are doing and planning to do it here in ESRIN, close to Rome, but in a fairly limited site, nevertheless, Professor David Larry has managed, in cooperation with the City Hall in Dallas, to deploy sensors all around the city of Dallas. So they are doing something which is a complicated name, but machine learning, multivariate, nonlinear, non-parametric regression. We have some things like this. We will work towards actually using much more machine learning for the calibration activities, and we are planning throughout this cooperation to get some of the know-how of David Larry's team to us, so that we can do a better job, of course. And besides that, so besides the cooperation on the AI and exploring the AI applications, we are also planning to exchange the data that we collect. So the data that we will collect with the AQPs we are planning to send it to them, and we are planning to get the data that they are collecting so that we will study application. We will have more data, of course, and we will be able also to have like a single website showing actually more locations of around the world. Yep. So I will hand over to Max again for a bit.
Okay, this slide shows the data analysis and remote control that we can do on each AQP. Each AQP supports data analysis and possible to calculate any kind of math functionality. As I said before, we use the Python, and importing math library Python can do any kind of mathematical function. So it's really easy nowadays to program to calculate the main statistic values. And this kind of a platform implements our regressive model, even some kind of a library, for instance, scikit-learn or TensorFlow. Scikit-learn is free, so it's possible to make experiment, especially for the makers, and apply really complex, some years ago, really complex algorithms even to make a graph and to understand what is doing the kind of platform or the behavior of the sensor. Anyway, when we use a low-cost sensor, we can't make scientific measurement, of course, but using machine learning algorithms, big quantity of the data, nowadays we call big data, is possible to understand the limit and to improve the measurement. Chip sensor has got two main problems. The first one is we don't know the accuracy of the measurement. In principle line, when we make a measurement, we have to know the value, the results of the measurement, and we have to know the error. In this case, with the chip sensor, we don't know the error. So if we use this kind of device for comparison, we can improve the quality of the measurement, and then we can define even the error. The error can be small or big, but anyway, we have to know the value of the error. Another problem that has this kind of sensor is the stability during the time. So we need to check this kind of sensor, every year or during the time, because it's not clear the behavior of this sensor. Anyway,
yes. So now I will give Max some time to prepare the demo, in particular of the Lotus, but we will see. We have about half an hour, so we can demo different things. So while Max is preparing this, I will just show you a couple of screenshots of the. It's not very important that you see all the details of the images, but this is examples of things that we are able to measure and analyze, if you want, with the Arable Mark II sensor, so not the AQP. So we are talking about things like the normal weather, so the temperature, the humidity, pressure, and how this, not only the information that has been collected, but how it is forecasted to evolve. And also on the plant, the health of the plants with things like evapotranspiration. It's one of the things that is quite difficult to measure, but this device is able to do. And here on this one, we have just it's just an example of alerts. So a lot of alerts that we get from a device like that. For example, with things like rainfall and excessive rainfall. So this is from last week when there was a lot of rain in Rome. So we got a lot of alerts. And this one is other examples of graphics that we can get from the web interface of the sensor. So things like the NDVI, the vegetation index, leaf wetness, evapotranspiration, and chlorophyll. And also on the weather side, the evolution of the temperature and also cumulative precipitation. So in this one, probably you cannot see it so well, but we have, this is for the month of November, more or less, and we have until the middle of November, no rain at all. And then we started getting some rain, and then between the end of November, beginning of December, we had really a lot of rain. So that's one of the other things we can measure with this instrument. So now that's the end of our presentation. So we will move to the demo of the Lotus and other sensors by Max.
Okay. Now we show you a demo about the Sky Lotus. Lotus, we said, is a globe and opening as a lotus flower. Now we try to open this kind. As we said before, this platform has 6 petals, and for each petal we have sensors. Now we try to measure one parameter, that is, this parameter is CO2. As you know, we take oxygen and we emit CO2. And in this case, you see here the graph in real time.
Yeah, what we are going to try to show you is that these things actually work. No, there's not, because so far we have just been talking to you, presenting things to you, but these things actually work. So they actually have sensors which are able to give you a measurement, and we can monitor the trend of the measurements. And to show it to you that this actually works, we have a graph there on the laptop, and we have the sensors here. As Max was explaining, we have one sensor per petal, which is a very different configuration than you have on the standard AQP. And we have this one here, which is the CO2 sensor. And as Max was explaining, since it's something that we can breathe, we will show you how this evolves. Not only that, we are going to show you actually, this was not planned, and it's not something that normally we would do, but we can actually show how the efficiency of masks, for example. And I will do first an attempt with the mask on, and an attempt without the mask on, okay? So here we go. So there you see on the graph that the level of CO2 has gone up, but not so much. And now we will see what happens if I just remove the mask for a few seconds and do the same thing. And you see an incredible spike. A really, really incredible spike if you compare what happens when I do it without the mask and with the mask. So, of course, when Max designed this initially, the idea, we were not thinking about viruses and the masks or anything like that, but it is actually a very nice way of demonstrating that this actually works, that the sensors, they work quite well, even though they are low cost. We are talking about like €5 per sensor and things like this. They are very, very cheap.
Another thing that we can add is, you see this kind of trend of the sensor. Sometimes when we talk about the chip sensor, we don't understand the problem that they have. But for instance, in this case, we see a variation of the value of acquired by CO2. You see that this trend is physical value, physical variation. For instance, if you have something, a spike and finish, in that case, we can have an error. Instead, in this case, we have a variation, but even the variation follow a physical variation. It's not like a spike or error. So it's possible to apply machine learning on works in the first step of the theory, and then in the machine learning, then in the context where you are to try to correct this kind of error, or to try to align this kind of value to a real measurement. Another experiment that we can do is to use Tarko to measure the particulate. It's possible to make another small experiment. Now we close. This is clear the increasing and decreasing of this kind of value. Now we stop the sensor. We check another sensor, just a few seconds.
So, and one thing that Max mentioned in the beginning that maybe it's easy to forget is that the basic AQP with all the 3 levels and lots of small pieces of hardware, but lots of hardware in the end, and sensors, it doesn't have a way of showing the values of the trends of the values and the measurements. So that's why we have on one hand, you have a web server and the website where we show you the network of sensors and the evolution of the different measurements. But on the other hand, also for debugging purposes and actually to see if things are working, as you can imagine, we have much lower level interfaces, much closer to the sensor itself and the platforms themselves, which is what Max is actually using now to show you how these things work. So I was looking at on the chat window that some people were asking about the operating system that is being used, and we confirm it's the Raspbian.
Yeah, the Raspbian, the original one
of the RasperryPi. Yeah. So that's what you see. If we have it on the tablet of the Lotus. Yeah. So here, what Max has done is he has sprayed a lot of talc around the AQP, the Lotus AQP, which is not the CO2, but it is something else, which is also very important to measure, also for the air quality of in our cities, which is the particulate, and that's what you see. You also see a huge spike when
maybe a bit exaggerated on the quantity of the talco. Anyway, we try to use this platform even to verify the functionality of the mask. When we were during the lockdown, we were trying to we are talking about the maker experiment, the real maker experiment. We use this platform to measure. You see the value goes down, the peak over, and then we try to measure the functionality of this kind of a mask, because at the beginning in Italy were not possible to find many masks in the shop, and so people try to use the t-shirt and all that stuff. So we try to measure even the functionality of the t-shirt or other kind of material, and we just for case discovered that some kind of material filter better than other. For instance, the t-shirt doesn't filter at all, but it's another problem. Anyway, we use wood with a hole. We put in the middle the mask, and then we put something like a small fan, and putting the talco without the mask or with the mask. It was possible to measure the difference. How the mask were able to, or that mask was able to measure the functionality of this kind of experiment. That's all.
Okay, so this was the presentation we wanted to give, and the main demo we wanted to give you of the Lotus. If you have any questions, you can ask them on the.
Before closing, I would like to
sure.
something.
So we can either take questions and answer 2 questions, or we can show you some other
just because
some other demos. Yeah.
Even Lotus is possible if we see Lotus is okay. Lotus now close all patterns. There is even another, we call Lotus aperture. Then we close. And then the last stuff that we want to show you is this one.
Yeah, so of course, sometimes we also like to introduce some funny features into these devices. So, yeah, I think we will probably finish the slot now. If there are, I can take a quick look here if we have any more questions. We have someone saying that the sensor is cooled or non-calibrated, that the ppm, so the parts per million, in air free is about 415.
Last one. Yeah, exactly. This kind of sensor is needed to reach a temperature for working. The temperature is around 200 degrees, sometimes even a bit more. So this kind of sensor needs to be in working already in a way needed 2-3 days. So if we start at this moment, the value has to be stabilized. Anyway, it's possible for this kind of platform to calibrate even from remote the platform. But in this case, when we turn on, the sensor is completely cold, so the value is not indicative of the normal status.
Yeah, so these are the usual problems we have with this kind of sensor. So yes, I think we will close the session very soon. Just something important, which is not only a way to contact us if you want to contact us, but also to very important, the links to the manual, the links to the videos. So there is some information, quite a lot of information actually, on that we showed here, but of course it's easier if you can find it yourself on the internet. So the guide, the manual on how you can build your own AQP, the link on where you can get the software to run on the AQP, and also videos that show things in operation. Then there is actually a very good video of how you can assemble the different pieces of the AQP. So there is. I will try to check this because. Initially we signed up for the Maker Faire as a virtual stand, and this was what we were trying to do yesterday, and today we changed to this slightly different format of a talk, which works well, no problem at all. But it might have happened that some of the information that we had entered in the Maker Faire website about the stand and all the links to the information and all the things that we are doing, there was quite a lot of information there. It might be that you don't find a direct link from the talk today to that. So we will work, and between today and tomorrow, we will work to see how to point properly to the information and how to make sure that it is easy to get to. And of course, we will repeat this tomorrow at the same time, so from 2:30 to 4 Central European time. And for our contacts, I think probably the best thing is that we put them on the chat window there. So if people want to write to us. Yeah. So I will write here.
Now I use this kind of time to show you describe this kind of platform. We made this piece with the 3D printers, and even to test quickly, we made this kind of support. So it's possible to insert the sensor and with a specific software test really quickly this kind of sensor.
Okay, so we hope you enjoyed being with us this afternoon. And if there was something that you didn't really understand or would like to know more information, I left the contacts on the chat window. And you can also join, of course, again tomorrow if you want. We will, more or less, the talk will be the same, but we will maybe think about some other things that we could show. But so we hope that you enjoyed and have a nice afternoon.
Bye, thank you.